Right, good morning, ladies and gentlemen. I'm Christopher Palmer, and it's my job to give you 4 lectures on data analysis in preparation for the laboratory course. This lecture course has 4 lectures, 1 this week, 2 next week, 1 in 3rd week, so that you've had the whole course before you start your individual labs in week 3, because you've got 2 weeks of training sessions between now and then. It used to be called errors, which sounded rather dull, so I gave it the absurdly overblown title of data analysis. Unfortunately, the content is the same. It's actually about errors. So the first 2 lectures are mostly about analysis and assigning errors to a single data set. The 3rd lecture will be about combining 2 data sets, broadly speaking, straight line fitting, and the 4th lecture will be a discussion of how accurate all that procedure has been. For those of you that haven't discovered yet, the way you find lecture materials is you go to the lecture list, you click on the lecture, so there's today's lecture, and then you click on the lecture materials, and that takes you to my website. And then you have a range of stuff that you can go to, including data analysis lectures. So you'll find some lecture notes in 2 versions. Some material was removed in 2018, but it's still, so I left up the 2017 version. And there is a problem set. It's most unlikely that any tutor will set that problem set, but it's worth taking a look at. It's supposed to be interesting. They're kind of brain teasers as much as anything. And there's some background material to some of the experiments that I'm going to be talking about, and there's a solution set for the problems if you need it. And there's something else at the bottom which I'll refer to a bit later on. So let's get rid of that. So, broadly speaking, physics honours theorists more than it honours experimentalists. If you think about the physicists that you've heard of most of them because they understood something and propounded a theory, wrote down some equations that described a phenomenon. There are a few honourable exceptions. 2 immediately spring to mind, both Americans from the early years of American physics, Michelson and Millikan. Has anybody heard of Millikan and know what he did? Well, if you read up there, it'll tell you. Yeah, there's the oil drop experiment. That's not the only thing he did. He did after he finished that, he did another even more brilliant experiment, which I'll tell you about a bit later on. And the Clarendon's own Harry Moseley, who is another brilliant experimentalist. So those are some obvious examples from the early years of the 20th century. That's a good period to take examples from, because a modern experiment is almost entirely digital. Everything, all the signals that need to be recorded are digitized at the earliest possible opportunity, and all the analysis is done digitally. And there are usually then many data streams that have to be combined and understood. And that's clearly a very complex problem, and it's much too complex for an introductory set of lectures. So in a lecture, in an experiment of 100 years ago, the number of actual bits of recorded data is so much smaller that we can understand the whole thing and see how the errors operate within that context. So, just over 100 years ago, Millikan did the oil drop experiment, which I'm sure you've mostly heard of, showing that charge was quantized and measuring the value for the electronic charge. And the value that he got is given there. It's 1.5. Well, he measured it in the units of the time, so he gave it in electrostatic units, which were the prevailing units then. But converting it to coulombs, he gave the answer as 1.592 times 10 to the minus 19 coulombs. So let's think a little bit about what that means. It clearly doesn't mean that the charge on the electron is exactly that number. But what does it mean? Perhaps the number of significant figures that is given is telling us something, and it means that it's bigger than 1.591 and less than 1.593 times 10 to the minus 19 coulombs. So that range of plus or minus 1 in the third digit is a significant range in his result, but it's not telling us the error. It's telling us something else. It's called the precision. And the precision is the least... What's the form of words I used here? The least distinguishable change in the result. So the number of digits gives you the precision. In this case, it's plus or minus 0. Well, it's 10 to the minus 3 times 10 to the minus 19, which is 10 to the minus 22 coulombs. And normally that would be related to the accuracy, but the accuracy is a different number. Is the, what's the form of words I've used? The difference. Between result and the true value. So really, the error is really more to do with the accuracy of the experiment than the precision with which the result has been quoted. And of course, Millikan, as a great experimentalist, gave an error. Now, he gave that using the nomenclature of the time, which I haven't gone into in detail, so I can't exactly tell you what his error corresponds to as a standard deviation, because that's not the form of words that he uses. But what I think it means is that the error is 2 times 10 to the minus 22 coulombs, or 2 in the last digit. And can I draw your attention to that notation that I've used there? This is a very convenient way of giving errors as part of the value. So the value that I'm quoting there is 1.592 brackets 2 times 10 to the minus 19 coulombs. So the number in brackets is to be interpreted as an error on the last quoted digit. Had he counterfactually quoted another digit, suppose he'd given 1, 8 instead of 2, and he'd given the error, he might have then given the error as 17. Okay, so now it's 17 in the last digit, which is pretty well equivalent to 2 in the digit. So maybe that's actually what he measured, and then he thought, actually, I don't know that last digit isn't really doing anything. I might as well round the whole thing. I'll round that up to 2, and then I'll round that up to 2 as well. So you can give 2 digits there. You can give a number greater than 10 there, and that will still apply to the last digit and give you the error in the last digit. So, does that mean that the charge on the electron lies between 1.590 and 1.594? No. We're getting closer. Every experiment, if you took enough measurements, and this is an idea we're going to use an awful lot, the idea of the population of possible measurements that you could take in an infinite amount of time. So if you had an enormous number of measurements and you plotted their values, they would form some distribution. And the example up there is an example of what's known as a normal distribution, and those of you that did statistics module in maths will recognise that. So the important point about that function is it doesn't have a hard cutoff. It has long tails. The tails are exceedingly small because the functional form is e to the minus x squared, so that the tails die away very, very rapidly indeed. But normally, the number that you quote is one standard deviation, which is a concept I shall define more carefully shortly, which is shown by this solid line here. So those, and you'll see that the probability, the areas on this under that curve are to be interpreted as probabilities. So the probability of lying within plus or minus one standard deviation, say for example plus or minus 10 to the minus 22 coulombs, is for a normal distribution some fixed number, which is 68%. For two standard deviations, which is shown here, it's the bulk of the distribution, it's 95%. For three standard deviations, which is also shown, but it's so low, it's so close to the axis you can barely see it, it's 99.7%. So the best practice is to give a standard deviation and to say that it's a one standard deviation. And if you give a number which is a multiple of that, that's known as a coverage factor. So that if you quote two standard deviations, so that you're confident that you're 95% confident that the answer lies within two standard deviations, then you absolutely must state that the error is two standard deviations, because the default would be that the number that you quote is one standard deviation. So however you interpret Millikan's error, you're going to struggle to get it to be consistent with the modern value of E, which is 1.602 times 10 to the minus 19 coulombs. And that is quite a lot of errors. That's 5 standard deviations away from the number that he quoted. And that's a very interesting fact, which I'll return to a bit later on, and I'll tell you why that's true. So, when you start doing labs, you'll find the demonstrators keep saying, yes, but what's the error? Show me the error, display the errors, calculate the errors, propagate the errors. They'll go on and on and on about errors until you're sick to the teeth of it. That's because they're quite important. How important is the error? Well, I think it's become steadily more and more important over the last century, and partly because of Millikan's mistake in this experiment. And once you start being able to measure different combinations of the fundamental constants, the number of fundamental constants involved in most physics is quite small. The charge and the mass of the electron, the mass of the proton, the speed of light, Planck's constant. You're struggling to find another one, okay? So you can measure those in different combinations, and it rapidly became clear that the values that people were quoting for the different combinations of the same constants were not consistent with each other, because there were errors in their experiments that they hadn't understood. So errors, the importance of understanding the errors in your experiment has become more and more and more important, and it's now very important indeed. And in two cases, it's actually far more important than the actual result. The first of these is what's known as a null experiment. So if I were to say, for example, the speed of light in vacuo is the same in all directions, or the charge on the electron is equal and opposite to the charge on the proton, or the force between two charges varies, or two masses for that matter, varies as the inverse square of the separation. Now those statements contain an awful lot of physics, but they're not numerical statements, they're statements of principle. The question is, what are they based on? And in each case, there's been an experiment saying, let's postulate some effect which would mean that this was not true, and then measure the size of that effect. And the expected size of the effect is 0. So you're measuring something which you expect to be 0. That's called a null experiment. So in the case of the speed of light being the same in all directions, the experiment is the Michelson interferometer, the Michelson-Morley experiment. In the case of the inverse square law between masses, it's Cavendish's experiment, which used to be an option on the practical course in a later year. I don't know whether it still is. It's quite a delicate piece of apparatus, but it's you can measure the exponent, or you can measure the difference in the exponent of that power law, 1 over r squared. You can measure the difference from 2. And so you say, let's suppose it's 2 plus epsilon, we can measure epsilon and get a number for it. So in that case, the experiment will give an answer which is consistent with 0. But the interest in the experiment is in how small could that effect still be and still not be detected by the experiment. So the interest is really not so much in the answer, but the result, but not so much in the number, but the error on the number. Another example of an experiment where the errors are kind of more important than the number itself is what's known as secular variation, which is things that vary very, very slowly over time. There is a current, there have been repeated current proposals to imagine that the fundamental constants vary with time over the age of the universe, and you can test that by looking at things in looking at spectral lines originating from very distant astronomical objects, for example. So this is a classic example of the measurements of the obliquity of the ecliptic. I don't know how much old-fashioned astronomy you know, but you know that the Earth's orbit around the Sun lies in a plane, and the axis is tilted with respect to that plane, and the angle from 90 degrees is called the obliquity, and that sets the obliqueness of the Sun's passage across the sky. So it's called the obliquity of the ecliptic, because the path of the Sun across the sky is called the ecliptic. So the obliquity of the ecliptic was defined in late antiquity, and there are measurements that were collected in the 16th century of the obliquity at different epochs. So around about 150, a measurement from Ptolemy gave it as 23 degrees, 51 minutes, 20 seconds. He'd just done his own measurement using an apparatus fixed to the facade of the cathedral, the Duomo in Florence, of 23 degrees, 29 minutes, which is significantly less, which was interesting. And he collected a few other measurements from the intervening period. So the other 3 data sets there are from Arab astronomers in the Middle Ages, and it appeared to show that the obliquity of the ecliptic was decreasing. However, that clearly depended on the accuracy of the earlier measurements. All of these measurements, including Dante's, were done with naked eye astronomy. And for if you're looking at something with a naked eye, a minute of arc, so 1 in that second column, the 1 minute of arc is a very, very small angle. And anybody claiming to do anything with seconds of arc is kind of quite pushing it a bit. So none of them had quoted errors on their value. And so it was a hypothesis that the obliquity was decreasing. And it took an awfully long time to sort it out. It prompted a research program that was lavishly funded by the Catholic Church, involving measurements in the way you measure, well, a very good way of measuring the obliquity of the ecliptic is to take a very large, dark building in a sunny country, think cathedral, right? And then you take a very small hole in the wall, on the south wall, which lets in a chink of daylight, which falls on the beautiful Renaissance pavement inside the cathedral to form a little splodge of sunlight, a little disk of sunlight. And the distance of that disk of sunlight from the wall tells you the angle of the sun in the sky. So during the day, the disk moves, and so you can, and at the maximum, at the meridian, as it crosses the meridian, as it crosses the north-south line, it's at its maximum altitude, and a careful measurement of the distances gives you a value for the obliquity of the ecliptic. It's a method littered with systematic errors, which I'll talk about a bit later on, and it took, well, in fact, that method never produced really enough results of sufficient accuracy to settle this question. I'll return to that a bit later on in a minute. So the error is normally considered as an integral and highly important and much discussed aspect of an experiment now. So I mean, we're putting you through all this because you have to get into that mindset of thinking, can I defend this number? At what level can I defend this number? If somebody else measures a different number, which one of, is it possible that we agree even though the numbers are different because they're within the errors? All of that matters an enormous amount these days. To turn back to this probability distribution, this used the normal distribution, and as I say, if you'd done the statistics module at maths, you would have met the normal distribution because it plays a central role in statistical analysis. There is a reason for that, actually, which is known as the central limit theorem. I remarked earlier that most measurements now are digitized, all the data streams are digitized at a very early stage. So let's think about the error involved simply in taking a signal and digitizing it. Okay? So that's the only error I'm considering, is the digitization error. So to think of a very concrete example, let's think of a digital kitchen scale. Okay? So it weighs in grams. So if you put your flour on the scale and it says 80 grams, what's the probability distribution of the mass of flour in the bowl? Okay? Now it can't be better than it's measuring to the nearest gram. Okay? So if that is mass and that is 80 grams, it could be anywhere between 79.5 and 80.5. So the probability distribution function can't be better than that. Now it's quite likely to be a lot worse than that because it's not rounding to the nearest gram, maybe it's the rounding is asymmetrical, so this error box is displaced slightly relative to 80 grams. It's really telling you that but in saying it's 80, it's really telling you it's less than 81. So the worst case will be the whole thing is displaced over to here, so it's telling you it lies between 80 and 81. But it might be worse again because the calibration may not be ideal, so that if it's only being read out to 1 gram, the people who calibrated it probably didn't calibrate it to that level of precision anyway. But it can't be better than that. So if we just take that as being the best case that it could be. So you now toss in your 50 grams of butter. I'm afraid I'm old-fashioned in these things. The question is, what's the total mass in the bowl? So that involves adding together the number that you got from this weighing and the number you get from the other weighing. Let's assume we're weighing them separately rather than combined. We're weighing them separately and then putting them into a mixing bowl. We're not weighing them directly on the pan. Okay? So what's the error distribution on that? Now there's a little piece of mathematics here which I'll do rather simply. Suppose if the first measurement is x primed, then the probability of then getting a result y for the sum in a range dy is p of y dy is, so that second measurement has to take the value y minus x primed dy. Okay? So if you want the total probability of getting a result y in a range dy. That's the probability current. That's the probability distribution function in the two measurements combined. We have to sum over all the different ways in which that could happen. In other words, we have to sum over all the different values of x prime. Well, the probability of that route happening is p of x prime with a range there, dx primed. And so the result for the total experiment, for the sum y, is the integral, potentially over all values of x primed, dx primed, and dy is not part of that. So I'll factor out the y. So I'll now cancel the dy. Okay? So the probability function of the result involves doing that integral over the two probability functions of the two measurements. And that's called a convolution. I'll put the dx primed in its usual place. That's called a convolution. So the result of the result of two measurements is a convolution of the error distributions of each individual measurement. You'll meet convolutions next year when you do the Fourier, the mathematical methods. I don't think you'll meet them elsewhere this year. It's a very interesting function. You can show, for example, that it's symmetric. The fact that the order of the measurements is irrelevant. You can do a change of variable in this integral and have y minus x double primed here and x double primed there, and so on. You can play about with it. You can work out, if you want to work out the mean and the standard deviation of this, you'll find a relationship between the standard deviation of this and the standard deviation of the original function. P, you can generalize it to different error distributions for the two things here. If you were combining measurements made with different pieces of equipment, so you could have a P there and a Q there, and so on. Yeah, so this is just the simplest possible case. So the next slide, page 2, shows the... no, not that one. That one. No, not that one either. That one. Right. Okay. So the top one there shows the normal shows the uniform distribution appropriate to the single digitization. Whoops. And I've overplotted it with a normal distribution with the same standard deviation. Okay. And you'll see that the single digitization probability distribution is wildly different from the normal distribution. When you do 2, what happens is the result, the maximum possible error gets twice as wide. It's gone from half here to plus or minus 1 here, as is, if you think about it, obvious. There's a vanishingly small probability that both measurements were at the limits of the error distribution, and so the total error distribution. And it turns out, if you do that integral, you'll find you get a triangle. And that looks much more like the normal distribution. And if you add in a third one, so that it goes out all the way to 1.5 on this axis, then you'll see it's really very close to a normal distribution. And so there's a theorem called the central limit theorem, which says that approximately any probability distribution function that you're likely to get, if you combine enough of them, starts to look like a normal distribution, or at least in the middle of the distribution. These still differ from a normal distribution, rather importantly, in the wings, right out here, but where there's vanishingly small probability anyway. But in the central part of the distribution, it starts to look very like a normal distribution. So normal distributions are important not because they occur necessarily in any given measurement, because the final result will involve the combination of many measurements, and the normal distribution is appropriate for those combined values. Right, so let's start in with a bit of formality. And let's introduce, so we're going to be talking about measurements of a single quantity. And so that quantity has to be well defined. So it's at least possible when you set out to measure something that the thing you're measuring, the concept that you're measuring, doesn't really exist, isn't well defined. So if you talk about the radius of the Earth is not a sphere, so it doesn't have a radius. Okay, it doesn't stop you finding values for the radius in books because it's usually called the mean radius, and that might be well defined. Similarly, the length of something it might be well defined, but if it's a three-dimensional object, it requires its end faces to be parallel, plane and parallel, and then it's got a well-defined length. In other cases, it doesn't. So something that's well-defined on one length scale might be much less well-defined on another length scale, and that's certainly true of the length. So that something which has got an entirely well-defined mechanical length for workshop purposes, you can measure it to a micron with a micrometer and get a well-defined answer. If you want to use the end plate as a mirror, then it could be very, the length of it could be very ill-defined for optical purposes because you're measuring it with a much finer, on a much finer scale. So the question of whether or not the true value exists is an interesting and important question, and we're just going to assume that it does. So we're going to assume we're taking repeated measurements. So each individual measurement, I'll give a number, I. So we've got xi, and that's equal to a true value which is unchanged and constant, and an error which keeps changing. Now this is a slightly odd equation, because this number is known. This is what you just wrote down in your notebook. The division into these two numbers is and always remains unknown. You never know what the true value was. You only know kind of roughly what it was, and then if knowing kind of roughly what it was, you can say kind of roughly how big the error was. But you never really know that exactly. And so it's important so I mean that's why I'm using a different font to display it. It's not just a capital letter, it's a sans serif letter which I'm using to denote some kind of inaccessibility of it. So why is this happening, that when you do the measurement twice you get different answers? And it's first of all I have to try to convince you that it's even the case at all, because in my weighing example, if I weigh this thing several times on the same scale, I'll get the same answer actually. Let's think about how that weighing scales are actually constructed. There's some signal that's being digitized. Where do you think that comes from? There must be some kind of force transducer underneath the top pan of the scales, connecting it to the feet. And it's measuring the force between that's needed to support the top scales, the top pan of the scales off the feet. And it's producing a voltage proportional to that force. Okay, that must be what's going on inside at some level. Okay, I mean it's not big. I mean in the old days it'd be done with literally compressing a spring and you're measuring distances. But we're talking digital now. So let's talk about a realistic modern thing. We've got a force transducer producing a voltage. That voltage will fluctuate. It will have fluctuations on it. It will not always be the same voltage. If you were to measure that voltage with an analog meter which had 5 digits, the last digit would fluctuate. Okay? However, that's not what we're doing. We're putting it into an analog to digital converter, and which means that the digital value probably doesn't fluctuate. Okay? So digitization often masks what's really going on, which is statistical errors. What you ought to be doing in a high precision experiment, what you would do is you would digitize at a level with sufficient digits to see the noise, so that the number you get is not always the same. So fundamentally, there is some random process in the result of the experiment. You may, by the way your signal chain is constructed, be hidden. That may be hidden from you. But that is nonetheless what's going on. So the question is, what is causing that fluctuation in the voltage? And there are many, many reasons. So in the weighing case, the turbulence of the air will cause the upthrust on what's on the scales to fluctuate at some kind of milligram or microgram level. Similarly, if the thing is standing on a surface over a washing machine, then some kind of seismic disturbance from the washing machine is also going to produce, is going to be accelerating the feet, and that's going to produce random noise in the experiment. There are electrical processes which produce noise on electrical signals always. So electrical signals always carry noise due to what two processes known as Schott noise and Johnson noise, which you may learn about in due course. Having said that, I don't know whether you do or not. If you're doing a really high precision experiment in quantum optics, or well, quite a lot of areas of measurement nowadays are approaching the level where you're limited by the fact that the thing that you're measuring is constrained by some kind of quantum mechanical uncertainty. So there are all these different reasons why there are random errors in experiments. Now, I've used that word random quite a lot of times, and it's slightly ill-defined, but we can give some properties. I mean, presumably it means unpredictable. It probably means a bit more than that. And let's assume that it means that on average this is 0. That over a sufficiently long, so again we're introducing this concept of the infinite set of possible measurements. On some kind of infinite data set, the average of those errors would be 0. Now, it's easy to construct predictable models of what epsilon might do, which would have that property. For example, it might vary as a sine wave. Okay, so there might be some sinusoidal process that's going on that's affecting the result. So in the case of an electrical result, it might be mains pickup. So there's some 50 hertz has got mixed in with the signal, so that will still average to 0, but it's entirely predictable, and it doesn't have this other property that if the average of one measurement with another measurement, so if you take, for example, the average of measurement I and measurement I plus 1, or measurement I and measurement I plus 50, if that's the period of the signal, those averages may not be 0. And so random requires, at the very least, that the average is 0 and that these correlations between different values are 0. So one of the things we have to do, the first thing we have to do, is to understand how to handle statistical errors. Unfortunately, there are results that affect there are things that affect the result of experiments which are not random and don't average to 0. And I've referred to some in my homely example of the digital weighing scales because I referred to the calibration of the scale. And I've also referred to Millikan's oil drop experiment. Have you ever seen the analysis of the physics of the oil drop experiment? There are basically 3 forces in play. I mean, you know what? I hope you know the basic concept. You've got an oil drop in laboratory air suspended between a parallel plate capacitor, which can apply an electric field to it, and after a fairly short time, if it falls or rises, it will reach terminal velocity. And there are 3 forces in play. There is the weight. I'm going to take the up direction as positive. So the weight force is minus rho, minus 4/3 pi a cubed rho g. So that's the volume of the drop. if you multiply by the density, that's the mass of the drop. A is the radius of the drop, and multiply by g, that gives the force. So that's one force that's involved. There is the viscous drag force, which always opposes the velocity, which is minus 6 pi times the viscosity of air, eta A times the velocity v. And there's the electric force, which is the electric field times the charge on the drop. The electric, which is Q V over D, where V is the voltage that you're applying to the plates on the capacitor, and D is the separation between them. And at terminal velocity, it's moving with a steady, it's moving with a constant velocity, so there is no force. So these forces must balance. So we must have, at terminal velocity, QV over D minus 6 pi eta A V minus 4/3 pi A cubed rho G equals naught. Now, if you look at that expression, it's got lots of symbols in it. They're almost all constant. So the spacing of the plates, the charge, pi, the viscosity of the air. For a given drop, the radius is constant, although you won't know it for any given drop, the density, the gravity. So the only things that are in play here are the voltage that you're applying to the plates and the velocity. So I'll take the voltage as a control variable, and the x, and the velocity as what we're going to measure. And this is linear, so there's a v here, there's a capital V here, there's a lowercase v there. So that is a linear thing. It looks something like that. So there are two, that straight line is adequately defined by 2 points, and the two that are normally chosen for measurement are the intercepts, here and here. So this point here has 0 velocity. So this is the case where the drop is suspended, it's motionless, by the electric force. The electric force opposes the weight. So we have the velocity is 0, this term's 0, this equals that, and we get, so if you call that V equals V0 is 4/3, well, pi A cubed rho G D over Q. And this point here is 0 voltage. This is where you turn the electric field off completely and the drop just falls under gravity, and it reaches some terminal velocity, V0, in the downwards direction, of course. So the velocity is minus some value, and if you put that into there, you'll get some cancellation, and you'll get 2/9, and the pi cancels, and then A cancels A squared over eta rho G. Let me just check I've done that right. 2/9 A squared. Yes. Now, so there are the thing we're trying to find is Q. The only other thing in this equation that we don't necessarily know is A, and so I can get A here. So Q is here, so if I rearrange this, I get Q equals something involving A cubed, and here I've got the terminal velocity in this part of the experiment involves A squared. So if I take the 3/2 power of this expression, I get A cubed, which I can substitute into there. However, you'll observe that it involves the viscosity of air. And in fact, it involves the viscosity of air to the 3/2 power. And so, although the numbers that Millikan took were all perfectly coherent and correct, every measurement was affected by the error in his viscosity of air, and he was using a wrong value. And it was more wrong than he thought it ought to be. he knew, I mean, he obviously understood about systematic errors, but the error, it was outside the error that he was quoting. The error was actually wrong. It wasn't a systematic, it wasn't a statistical error in ESA. It was actually a wrong measurement. It was done in his laboratory, but not by him. Millikan was a brilliant experimentalist, and everybody trusted him, and his value for the electronic charge was used for the next 20 years or so, but it rapidly became clear that there was some problem in the fundamental constants somewhere, that these different combinations of the fundamental constants, when you measured them with different ways, didn't fit together the way they ought to. And by the 1920s, that is to say, what was the date? It's about 15 years later, there were two values of E in circulation. There was Millikan's value, and there was a value derived from spectroscopic data, which was called the X-ray value. And these differed by 0.5%. And in the 1930s, this was tracked down to Millikan's value for eta, which was 0.5%, which was a third of a percent wrong, and which got scaled up to a 0.5% error by the time you took the 3/2 power. So that now that is an important difference, you see, between a statistical error and a random error and a systematic error. That after the event, 20 years later, they could recalculate what Millikan should have calculated just by using a different value for the viscosity of air. The statistical errors are all unchanged, it just changes the value of the result. So the statistics are all exactly the same, but the numbers slightly different. So that's a real important distinction between a statistical error and a systematic error. But in principle, that you may be able to recalculate an experiment with improved value for some of the constants that are being used. There's a more modern example of that. Were you all taught in school the SI definition of the ampere? The thing about the force operating in vacuo between two long straight wires, all this business. There is a systematic constant which is common to all high precision experiments, which is the ratio between the current as defined and the actual current that's used in standards laboratories to calibrate meters. So there's something called the realization error of that constant. It was called K sub A, I think, the calibration constant for the amp. And it was common across a whole range of experiments that all depended on very high precision current measurements, and they had to depend on the standards the current standards that were in use, and so it was a systematic error that was common across many experiments, and it was a symbol, and it had a name, and it was actually evaluated in the evaluation of the fundamental constants. So that's the nature of a systematic error. It's something that's much bigger than it's potentially something that's much bigger than the experiment itself. It's something that's actually unknown. Now, what we're going to go on to talk about is how to analyze the statistical part of the error. We're going to give much less attention to the systematic part of the error. But actually, that in a well-designed experiment, the systematic error will probably be the thing that limits how accurately you can get. If by taking more data, we shall discover that you can reduce the statistical errors, but you can't reduce the systematic errors. So you can, in principle, reduce the statistical errors to the point where all you're left with are the systematic errors. So you really do need to understand them. And so the equation that I wrote down a board ago has to be complicated slightly. We have to split up the error into two pieces: a random piece, which has average 0, uncorrelated, it can be handled statistically, and a systematic piece, which we don't really know. We can say as much as we can about how big we think that systematic error is, but we can't know anything about its number. And so, in fact, we can't even quote a value for sans serif capital X. We can only quote a value for the the result of the experiment is this unknown value plus the systematic error. So what we actually measure isn't big, bold sans serif x, it's little, bold sans serif x, which is contaminated by systematic errors. And from now on, that's the thing that we're heading for. We're going to give, how do we give the best possible answer for this systematically contaminated result in view of the statistical errors that we're going to deal with. Now, I ought to warn you that what I've just said is not standard. That is to say, there is an international standard from the BIPM, the Bureau International des Poids et Mesures, the International Bureau for Weights and Measures, who are the people who ultimately have control over the units that we all use. And there is a BIPM standard for measuring errors, which is on the web page. There it is. It's a legal text. It's quite dull reading, but somewhere at a fairly early stage, it gives a little summary. I think it's here. Here we go. Clause 8 has a succinct summary. So let's go to Clause 8. Summary of procedure. So express mathematically the relationship between the thing you're measuring and the thing it depends on. Well, that's fairly obvious. Now, where's the important... The method they're proposing divides errors into two classes which do not map onto statistical and systematic. They are, and it's the classes that they use are measurements which are evaluated using statistical methods and errors that are evaluated by other means. They call those type A and B. And A and B do not map onto what an experimentalist would refer to as systematic and statistical errors. So there is, they actually say that the use of the term systematic, oh, it's not here, it's somewhere else, bother. It must have, yes, okay. Those which are evaluated by, so Class A are those which are evaluated by statistical methods. Class B, those that are evaluated by other means. Not always a simple correspondence between A and B and the previously used, they really think that they're changing the system here. Previously used classification into random and systematic uncertainties. The term systematic uncertainty can be misleading and should be avoided. Let me tell you that the people doing the most sophisticated, most data-intensive experiments in the world, who are, broadly speaking, physicists, aren't listening. Okay? I doubt if they even know the existence of this document. So if you're doing a measurement which is tied into some standards laboratory or some procedure for re-evaluating a fundamental constant, you will have to present your results in this fashion. So you should probably know the existence of this method, but it's actually not what physicists use. Don't ask me why, I don't know. Right, so now we have our set of data xi, which are related to something that we're trying to measure, which was called big, bold, capital X, and is now called little, bold, capital X, because it's contaminated with systematic errors. And there are three questions that we could ask, sensibly. One is, how accurate are the measurements? How good an experiment am I doing? What's the best result? And how accurate is the best result? Now, students, for reasons that I find perplexing, find questions 1 and 3 hard to distinguish. If you do an experiment, you get a number out, a single number, that has some error attached to it. If you then do it 20 times, that took you 20 times longer. Now, why did you do that? It was because you wanted a better answer. So there are two different answers involved here. There's a single answer from the data, and there's the answer from combining all the data together. And those have different errors. It's as simple as that. I can't say it's simpler than that. So those are the three things that we need to know how to calculate. Now, the accuracy thing, and this is literally the last thing I'm going to say, we defined at the beginning for these random errors that the expectation value was 0. The expectation value of two of them, different ones, was 0. But there's one possible, this is for I not equal to j, but there's one thing that we haven't defined, which is the average value of the square of the error. Now that cannot average to 0 because it's positive, and that is called the variance of the data set. And because it's an error squared quantity, if we're talking about masses, this has units of kilograms squared, and its square root is a standard deviation. So that is the definition of the standard deviation in principle. And it involves this slightly fictional universal average